Hello everyone, welcome to my Physics 2 lab report where we had to deal with bar magnets for our fourth ever lab. So let's get on with it. The purpose of this lab was to just investigate the magnetic field of a real bar magnet, and then afterwards we compared it with an ideal computational dipole model. And what we just did is just see how real magnets follow idealized magnetic behavior. And we observed it by utilizing our phones, by taping them to a ruler, and then measuring them from a bar magnet to see how a magnetic field is affected. So of course, the materials we use is under there, which I'm not going to really go through. And of course, here's our equations and models that we use. Here's the normal way of finding a magnetic field. Well, this is finding a magnetic field of a bar magnet, which could be acted as a dipole. And here's the distance dependence formula that we use during our report, and I just wanted to add that along there. So some assumptions that we had is just human error and device calculations. Coach, of course, can't fix that. The bar magnet has to behave like an ideal magnetic dipole. They're both equivalent to each other. The magnetic field follows the dipole field equation. That makes sense. Environment has negligible to no external magnetic fields. We have to find that out. And measurements taken and the consistent coordinate system is just defined consistently or just taken far enough to avoid saturation. So for our actual experiment, here's the major 2 points that we had to look through and see how it's affected. And here's our actual experiment as to how it did. I think we did pretty well to try and get things done, but I feel like we could have done a little bit better. Um, so of course I would rather be focused on B net being 7.228. So that's kind of where I want to focus on right now. So, of course, we did it on a computational experiment, and here are the coding that we had to figure out, creating the magnet, editing the function of the magnetic field. Then we had to visualize it from both the observation axis and the observation perspective. So here's the observation axis, and over here's the observation perpendicular. And then afterwards, we had to just visualize the magnetic field from it. So this is what we got for our computational, and as you could see that at B of 45 at this is D, you could probably say that this is around 10, 10.10, maybe 11, depends on how you say it, but that's kind of a bigger, at least a 4 point something difference from what we see over here. So really, in this experiment, the whole entire magnetic field of the bar magnet was at least predicted and almost the same as the physical magnet that we did in our investigation, but it was considered stronger. And maybe I blame my own coding on that, but it still was considered probably going to be stronger, considering that there were some negligible magnetic forces that we had to face. And the computational model assumes the perfectly uniform magnetization. So we could count on that to be a little bit more correct. So what if our experiment had not been oriented to compensate for magnetic north? It wouldn't cause any big changes, but it would just have a systematic distortion that would have probably messed up our entire experiment. So it's kind of a nuisance, but we could have just done something else. Could have just, compensate for it. That's a little bit better. And what if the two identical magnets were stuck together end to end? Well, attaching two identical bar magnets would give twice the magnetic dipole moment. So we would probably assume that there's a stronger magnetic field that's coming around it. So it's a little bit small irregularities that we'll probably have to test, and I hope we could do that for our next report, which I could check on later. So thank you for at least listening to my lab report, and I hope you have a blessed day this weekend.